Well, this is my first time at this conference, and I appreciate the opportunity to be here. This is joint work, and we're addressing a fundamental question in this paper. We've got lots of different asset pricing models that try to explain why expected returns are what they are, why the differences are what they are across securities. And we'd like to know which is the best model. We'd like to be able to establish statistically that a certain model is better than other models. And that's the basic question. So to put that in context, we have lots of different ways of testing whether a model holds, which means we can test whether expected returns are exactly linear in the betas that a model suggests should be explaining expected returns. But researchers seem to want to go beyond that. It's not enough to just test an asset pricing model. Presumably, none of these models are going to fit exactly. So if a model is rejected, we'd like to be able to go further and say that the model is a good fit, the model is a lousy fit, the model is better than other models. So that's what we'd like to be able to do. And many researchers, prominent researchers, have reported the cross-sectional R-squared for average returns as a measure of goodness of fit. You know, R-squares are used all over the place. They're intuitively appealing. Okay, so in this context, it makes sense to use that R-squared measure for the average returns because we're trying to explain expected returns. Okay, so the only trouble is the literature and prominent papers like Letow and Ludvigsen and Jagannathan and Wang and so many other papers have used this statistic, but usually we just see the point estimate of the statistic and we don't have confidence intervals, we don't have an ability to do statistical inference. So that's what we're going to try to do here. Now, in a previous paper with Stefan Nagel and John Llewellyn, we look at inference about R-squared, but strictly through simulations. So in this paper, we're going further and getting the asymptotic distributions and using them to do the inference. Okay. So we get the asymptotic distribution of R-squared, but since we're interested in comparing models, we look at the difference of R-squareds, the sample R-squared, and we have the asymptotic distribution of that as well so that we can compare two models, say which one is better if there's enough power. Okay. Okay, we also do some multiple model comparison, but I won't have time to get to that, but it's in the paper if you're interested. I should say that when we're estimating, say, two different models, we're using the same returns over the same period, so the parameter estimates for the two different models are likely to be correlated, and our asymptotics will take all of that into account. Okay, so the basic framework, we've got returns, factors, regress the returns on the factors to get the betas. We form this X matrix consisting of a unit vector and the betas, and that's going to be our matrix of explanatory variables. We're looking at models which all have the same form in terms of they're trying to predict the expected return vector using a linear combination of the columns of the X matrix. So the coefficients on the betas are the risk premia, the coefficient on the unit vector is the zero beta rate, usual setup. Okay, now we're entertaining the possibility that all these models are misspecified, meaning they don't hold exactly. So in that sort of case, there isn't going to be any gamma value, any gamma vector that makes the model hold exactly for all securities. So what we do in that context is we pick the vector that gives the best fit to the model, and we use both OLS weighting and GLS weighting, typical. Okay, the deviations from the model are the expected returns minus the model's prediction. And Q is the weighted sum of squared deviations from the model. That's our measure of fit. And the R-squared measure is going to compare that to the Q0 measure, which is the same sort of deviation sum of squares, but with only a constant in the model, usual R-squared thing. And that's the population, R-squared. And all these parameters, this is all population. All the population parameters will be estimated with the corresponding sample moments. Okay, so when we compare competing models, it's important to distinguish between nested models and non-nested models. Non-nested means we may have some common factors, but each model has some factors that the other model doesn't have. So, for example, the various consumption CAPMs that we look at are non-nested relative to the ICAPM specification I'll show you. In the nested case, all of the factors of one model are contained in the factors of the other model, and then the bigger model has a few extra factors as well. Okay. So, for example, the CAPM is nested in the ICAPM. Okay, now we have an important proposition, we think it's important proposition for nested models, which seems to be overlooked for the most part in the literature. It is touched on at an intuitive level in one of the Jagannathan and Wang papers, but there's no formal development, so that's what we have in this proposition. So here we're looking at under what conditions, when we're talking about nested models, under what conditions will the bigger model and the nested model have the same explanatory power? Meaning, under what conditions will the extra factors in the bigger model buy you nothing in terms of extra explanatory power, in terms of the cross-section of expected returns? So we want to know when that's true. And the answer is if and only if the vector of coefficients associated with those extra factors is equal to 0. Now, that may sound obvious, so why do I call it an important proposition? The part that maybe is not so obvious is that we're talking about the coefficients on the relation between expected returns and the simple regression betas on the various factors. The literature almost exclusively focuses on the multiple regression betas in a factor model. But those multiple regression betas and the usual notion of a factor being priced if its gamma is not equal to 0, that won't answer this question. It may answer other questions, but not this one, not the issue of incremental explanatory power. So I'll have an example of this and come back to this in a little while. When I put a box around something, you know I'm really serious about it. So, you may not be able to tell from my voice, but the boxes will. Okay, so the models are the CAPM, the labor income version of the conditional CAPM, which has a market factor, a labor income growth factor, and then this Prem factor allows for the possibility that conditional betas and conditional market risk premia co-vary over time. Then there's the Fama French model. If you're not familiar with that, you probably are in the wrong room. The ICAPM of Merton, there's a particular specification by Petkova that we look at. She looks at innovations in various predictive variables that have been used in the literature, and those innovations serve as the factors in this in the factor model. So there's a term spread factor, default spread, dividend yield, and a T-bill rate factor, risk-free rate. Okay, then there's the consumption CAPM, as usual, non-durable goods and services. The growth rate of that is the factor. There's the K version of the conditional CAPM due to Letow and Ludvigsen, which conditions on that consumption to wealth ratio. So we have the K factor, the consumption factor, and an interaction factor between the two. We have the ultimate consumption model of Parker and Juilliard. Ultimate here refers to consumption, not to the model, although they may feel differently about that. So by ultimate consumption, what we mean here is that we're taking into account the idea that stock returns reflect information very quickly, whereas measured consumption, you may not see the implications of some new information for quite a while in the measured consumption variables. So they look at consumption growth over a 3-year period, and so we're correlating returns in a given month with consumption growth in that month and 35 future months. So that's what the betas will reflect there. And then finally, the durable consumption model of Yogo, which has a market factor, the usual consumption factor, non-durables, and a durable consumption growth factor, which tends to be quite cyclical, and that plays an important role in that model. Okay, how much time have I got? Oh, good. I didn't realize this was a live webcast. I hope there won't be any wardrobe malfunctions here today. Right? Yeah. Okay, so we start estimation with von Macbeth two-pass method. Everything begins with von Macbeth. We'll be using full period betas with portfolios. We go beyond von Macbeth in that we adjust our standard errors for the risk premia for the fact that there's the errors and variables problem related to the betas. That goes back to an earlier paper I had. And we also adjust the standard errors for the fact that there may well be deviations from the expected return model. That's an idea that was introduced in my 2007 paper with Gofu Zhu. It's not commonly recognized, but if you're estimating a linear expected return relation and that relation doesn't really hold, that affects the sampling distribution of the risk premia that you estimate, and I'll show you examples of that. Okay, so the main results, we've got that the cross-sectional R-squared is asymptotically normal if the true R-squared is strictly between 0 and 1. If it's at the endpoints, if it's a useless model or a perfect model, then you have to treat those cases separately, and we do. And we test those hypotheses. When we want to do model comparison, which is the main point of the paper, we need to look at the difference of two sample R-squares for two different models. And we look at the asymptotic distribution under the null hypothesis that those population R-squares are equal for the two models. And we see if the data are consistent with that. And we have a lot to say about these asymptotic distributions, but there won't be time, so I'll simply say that the nested models and non-nested model cases have to be treated separately, and they're different asymptotic distributions. Okay, so the data, we've got returns from 59 through 2007. We start in 59 so that we can test all the models over the same period with monthly data. We'd like to use monthly data because the asymptotics aren't quite as reliable in small samples. So we've verified that with monthly data, sample sizes like this, the asymptotics work pretty nicely. Okay, as our test assets, we use the 25 size book-to-market portfolios of Fama French, but we throw in 5 more industry portfolios based on the recommendation in the paper I did with Stefan and John, because that challenges the model in a way that just using the 25 portfolios doesn't. We'd use more industry portfolios, but again, there's a concern about asymptotics here. You can't use too many test assets under the current framework. Okay, so since misspecified models may work well on some assets and badly on other assets, we do some robustness analysis, and we use 25 size beta portfolios. This is similar to what Fama French did in the 92 paper. So, okay, so some results here. Get out of your way. Wouldn't want you to miss anything here. Okay, so we've got the 8 different models along the top. The first row has the sample R-squared measures for each model, and 3 models clearly stand out, are separate from the rest. The durable consumption cap M, which I'll just call D cap M, the I cap M, and the Fama French model. They tend to be pretty close and pretty high R-squared measures. Now, their standard errors, these are computed under the hypothesis that the R-squared is strictly between 0 and 1 again. Those standard errors are certainly bigger than the differences between those 3 R-squares, non-trivial amount of estimation error. And if you look at some of the other models, you've got standard errors in the ballpark of 0.2 or even almost 0.25 for an R-squared measure. That's pretty, pretty imprecise estimation, but that's the point, to know how precise your estimators are when you report them, so that you can take that into account in interpreting those estimators. Okay, what else? We can't reject, this is the p-value for a test of whether rho squared, the R-squared, is equal to 1, the population R-squared. So we can't reject that hypothesis for D cap M and I cap M, but we can reject it for the Fama French model with a pretty small p-value. So, does this mean the Fama French model is a bad model? No. You can't use p-values as if they're measures of goodness of fit, because a p-value, it will reflect deviations from the model. It'll be influenced by that, but the p-value will also reflect power, precision. So you might have relatively small deviations, and it's a pretty good approximation of the model, but if the deviations are estimated very precisely, you may reject the model a lot and get small p-values. So you need a different kind of test to compare models, and that's what we're developing here. 1 minute?
10 minutes.
Oh, wow. Scared me for a second there. Okay. Okay, what else here? Oh, right. So as an example, the labor income model has a much lower R-squared than the Fama French model, and yet it has a much bigger p-value, 0.05, as opposed to something close to 0. But that doesn't mean it's a great model. It's very much influenced by the fact that the standard error of the R-squared is about twice as big as the standard error for the Fama French model. So those are the kind of things you need to take into account. Okay, in terms of the GLS results, we get lower R-squareds. You can think of the GLS analysis as kind of testing the model on transformed assets, where the transformed assets in general will have potentially complicated long and short positions, and these models just don't do as well on those kinds of assets. In principle, a model that's really correctly specified should work for any of these assets, but we don't have that luxury yet. Okay, so again, it's the same 3 models that stand out as the top. The rankings differ. Now Fama French is on top. We can reject that all those models are perfect fits, those 3 models, and we reject all the other models with p-values virtually equal to 0. Okay, so risk premia. We've got 4 models with significantly positive risk premia after we take everything into account. But what I want to focus on is this issue of model misspecification and how it impacts precision. In the paper with Gofu Zhu, the examples we looked at all had traded factors, and it doesn't really matter much for models with traded factors for reasons we explain in the paper. Okay, but with non-traded factors, for example, the term spread innovation, you can see that the Phong-Macbeth t-statistic is over 3, but then when you adjust for errors and variables using either my approach or Jagannathan and Wang have an approach that followed up on mine, that lowers the t-statistic a fair amount. But then if you go further and adjust for potential model misspecification, which is what the PM statistics are, then it knocks it down quite a bit. And that happens often with non-traded factors. Okay, so same sort of thing with the T-bill rate factor, and again, the same sort of thing with the ultimate consumption growth factor. So it's important to consider that when you do this sort of analysis. It's not unusual to see papers that report tests of the model and easily reject the model, but they also discuss estimation of the risk premia, but they use the risk premia standard errors under the null hypothesis that the model holds. So that's a logical inconsistency that can be dealt with using the kind of approaches we've got here. Yeah, I should say also, I think I failed to say that we do everything under much weaker assumptions here than in the previous papers. Jagannathan and Wang allow for conditional heteroscedasticity. We're doing that for all our measures, and serial correlation can be accommodated also. Okay, the Fama-French model, traded factors, you see all these adjustments do virtually nothing. But there is something interesting to talk about here nonetheless. You can see when you look at the usual gammas, the coefficients on the multiple regression coefficients. In that case, the high minus low factor clearly stands out as the one that's significantly priced. Small minus big, no. But again, those won't tell you which factors you need in the model to maximize explanatory power in the cross-section. So if you look at the coefficients that would be associated with the simple betas, or strictly speaking, it's the covariances, but essentially it's the simple betas, there's a reversal here. Now it's the small minus big factor that is significantly priced, and high minus low is more marginal. And the way to interpret this is that, well, we can't reject that the coefficient on high minus low is 0. Of course, that doesn't mean it is 0, but if it's 0, a hypothesis that we can't reject, if it is 0, then that means that if we left the high minus low factor out of the model and just had the market and small minus big factors, we would lose no explanatory power in population. So that's kind of a surprising result, but hopefully it's kind of interesting. Okay, now the model comparison results. So in each row we've got a model. Each column we've got a model. We're reporting the difference of R-squares for the row model minus the column model, and then we have a p-value in parentheses testing whether those two R-squares in population are equal. So running out of time, we reject the CAP-M in favor of 3 models, but the I-CAP-M, its R-squared is 65 percentage points higher than the CAP-M. You're not going to see anything much bigger than that because the bound is 1. So in spite of the fact that we have this enormous difference in the sample R-squares, we struggle to even reject the CAP-M in favor of the I-CAP-M at the 5% level. So that's probably the most striking example of lack of precision and how it impacts the analysis. We reject the consumption CAP-M 4 times in favor of, you can see the models there. And in addition, the Fama-French model dominates the conditional consumption CAP-M at the 3% level there. So those are the OLS results. GLS, the Fama-French model really comes on strong in the GLS analysis. It knocks out 5 models. In addition, the D-CAP-M dominates the consumption CAP-M. and that's it there. Now our additional results, hopefully I'll have time to finish these. When we use the size beta portfolios, an interesting thing happens now. The conditional consumption CAPM, Lettau-Ludwigsen model, performs very well on these assets. So it just illustrates the obvious point that these kinds of tests can be very sensitive to which assets you use. I'll just leave it at that. Chi model did very nicely here, and even dominated the Fama-French model, which sort of fell in the rankings in this context. It fell to 4th place. Okay, a separate issue is that most of the zero beta rates for these models are in the ballpark of 1 to 2%, and the coefficient on the market beta for models that have a market factor are always negative. Now that's something that's been seen in a lot of other studies, but it's disturbing, obviously, and it raises the question, should we give a model credit for high explanatory power when that explanatory power is coming from coefficients that we don't really feel are consistent with the underlying theory? That I don't think has really been considered in the literature, at least that I can think of. What we do here to address this issue is we constrain the zero beta rate to be equal to the risk-free rate, which is common in the literature, so that the excess zero beta rate is 0. We use excess returns as our dependent variable and just leave the constant out of the cross-sectional regressions, and that amounts to constraining the zero beta rate. And what we find in that case, these were the results summarized from earlier, and the main change here is that the DCAPM moves into 6th place. It was one of the best models before, but it also had one of the highest zero beta rates, and when you force that zero beta rate to be equal to the risk-free rate, it just doesn't fit well, that model. The formal model comparisons, the Fama-French dominates a few models. The ICAPM doesn't even dominate the CAPM, although it comes close. Again, it's about precision. The ICAPM has the highest standard error of the R-squared. It's about twice as large as the Fama-French standard error. And I'll summarize now. The ICAPM and Fama-French stand out as the best models in this analysis, but it's not all glory for these two models. Although the ICAPM is never dominated statistically, it only occasionally dominates other models. So we can't enthusiastically endorse it and say it's beating other models all the time, because it's not. The Fama-French model beats other models very often, but doesn't do so well with the size beta portfolios. And some people would suggest that when it does do well, that's in part due to data mining. It's the one model that's not really theoretically motivated that we consider. And then the obvious, it's important to take precision into account here. Okay.